Um, I'm happy to um, introduce the next session here on forecast uncertainty and explanatory instability. And Alan Forrest is our first speaker. Alan, I've forgotten now your official title. You're working with the business school at University of Edinburgh.
Yeah, that's right. Business associate. So it's
This is very good, and very much involved in their model risk management program there, right?
indeed. No,
All
thank you.
right. Well, I will turn it over to you.
Yes, indeed. Joe and I have known each other for many years in various contexts. The Edinburgh University Credit Research Centre conference has been a great place to meet up and catch up. So when Joe said he had a new idea about explainability and stability, I was very interested indeed. And when he asked whether I could pitch in on it, I thought I might, but I found I couldn't keep up. So rather than attempt to hit the high speed that Joe has reached, and we'll be talking about in the second half of this half-hour session, I thought I would set the scene with a little bit of the more pedestrian research that I managed to set the groundwork. It's not as not to underrate the what can be done. It's simply to set the context because explainability turns out to be very interesting and very fundamental to model risk management. So I hope everybody can see my screen now. Um, I, I'll um, I'll just see what can. That's it. Excellent. Um, Explaining a model is a very natural feature of model risk management. It grows out of the need to have good, clear documentation and the ability to demonstrate that a model aligns to certain purposes, regulations, certain goals that are perhaps not metrizable, easily calculated or measured, perhaps softer, more general, more social goals. Um, and with the rise of AI and ML, this this need has become a lot more pressing. Classical regression models have a structure that makes them easy to explain. In a sense, that makes their validation, as we've done classically, very natural. Explainability, the ability to lay out the components of the model, describe how they influence the outcome in a very explicit, simple way, is a great strength in their validation. Um, that's a strength that AI, machine learning models just don't have, almost by definition. And the root of a lot of the difficulties with validation and our trust in these models is associated to the difficulty of explanation. So terms like explainability, interpretability, understanding have become touchstones, points, benchmarks for defining safety and validation guidance for AI machine learning models. It's as if we're trying to import into the new world the explainability, the simplicity, whatever baggage we can carry from the classical models. So explainability is part of our nostalgia almost for the old world. The problem I found very quickly is that there's no agreed definition of explainability. That is, there's no simple, a single definition that everybody settles on, but everybody seems to understand what explanation is in different ways. A very technical mathematical approach focuses on the model. It's the insight gathered from a variety of investigations and descriptions of the model. This is a particularly intense mathematical approach. Perhaps more social, explainability is a process that engenders understanding in a selected group of explainees. So it's about communication to particular people. Um, that's the view from above, two different views. But actually, in practice, we find that models are explained usually just by a list of a few factors or combinations of factors that influence the model output most strongly. Um, this is usually what is understood in technical articles, and it fits most closely with the mathematical model-focused interpretation of explainability. I happen to think that that model-based approach misses something. It misses 2 points, which I think are worth exploring. The first is that there is somebody who receives the explanation. Um, an explanation does not sit in a vacuum. It's not simply a quantity like a Gini or a root mean squared error that hangs onto a model and that's the end of it. There is somebody who needs to be receive the explanation, and that is a human, and they have particular requirements. It may be personal requirements, it may be technical or regulatory requirements, and it may depend on the context. It's not necessarily model focused at all. The other way to escape the model view is to also look at the outcome that needs to be explained. It's not just about the model output or the structures within the model. It's about what effect the model has on the explainee or what decision is important to the explainee. And it's these two extra features that are sometimes missed in the mix. I'm going to expand on this. So it's quite clear that explanations do depend on the explainee and the outcome or the decision. Let's take the classic case of a credit decision. A scorecard says, we decline your mortgage application. The customer is legally entitled to an explanation of that decision. The nature of that decision means that the top 3 or 4 factors in the decision might be useful information, but that's only the start. The person who's speaking to the customer has to create a story that makes sense to the customer, that uses these factors intelligently and in a way that gets the customer satisfied, and presents an action plan to the customer to improve the chances of a positive decision. This naturally touches on fairness, ethics, legal standards. Um, an explanation that says we've declined your mortgage because you're a woman is clearly very unacceptable, in fact, illegal. But it is in the nature of explanation, an explanation. And no bank could operate a model for which that was an explanation. And therefore, by through the explanation, in the context of an explanation, fairness and discrimination are also part of the mix. More technically, a pricing model leads to an unexpected sell decision, a market pricing model. It has to be explained to the operations manager. Why did this happen? What were the features of the model that led to the particular decision? What was the price set? What influenced it? How could we change our response to the model's recommendation? That's a different kind of explanation. It's to not so much to a customer, to a non-specialist. Nevertheless, it requires some interpretation. An IRB model causes a material change to capital allocation. That has to be explained to the credit risk committee. Maybe you've even been in this situation. Again, the factors, the structure of the model is important, but if it's going to be explained just here are the top 3 things that gave the number, then it's going to create more questions than answers. A breach of compliance is caused by a model. It has to be explained to the regulator. Again, a very different kind of context. Again, explanation is important, and how you present it. Again, the top two or three factors are just not going to cut it here. What's a good explanation? Well, there's a nice paper by Nauta et al. I think there's 4 or 5 different authors. It lists 20 different qualities of good explanation. And if you like lists of things, then it's a great paper to read. Interestingly, all 20 qualities start with co, as if they were stuck in 2 pages of the dictionary. Correctness, controllability, contrastivity, confidence are 4 examples, each covering different aspects of explanation. Is it true? Can the explainee interact with the explanation? Does the explanation tell us what might happen if we perturbed conditions? So a counterfactual sort of explanation. How credible and probable is the explanation to the explainee? The important thing here is that as you go through this list of 20 characteristics, the more you realize that actually the features of a good explanation are also the natural outcomes of a good validation. The things that we are aiming for in model risk management and in quality documentation are more or less the things that Nauta et al. Pull out in terms of a good explanation. So I have the feeling that explanation is actually a natural uh, view or outcome of good quality model risk management. So just to wrap things up, an explanation should, I think, extend beyond the model. The outcome has to be explained. A human explainee needs to receive an explanation. And the important thing is that it's no longer just something we tack on to model risk management. It produces, it reflects, it encapsulates many of the best practices of classic validation. The next section, Joe is going to say more about this close connection between model explanation and model performance. But before I hand over to Joe, I'm just going to reflect on 2 points, which are kind of open-ended. The first thing is that as soon as you have have an explainee, a human explainee, then a good explanation is a social engagement. The explainee must be satisfied, or they must be capable of escalating their dissatisfaction. We're giving the explainee power in this relationship. And a second thought, if fairness is a kind of explainability, and I think my previous example showed how this might be reasonable, we know that fairness is decided not by looking at factors in the model, fairness through unawareness, but through far more subtle correlations and correspondences, trends, nuances. Should we be ready to give explanations using factors that are not explicitly in the model? And on that open-ended theme, I'll finish and hand over to Joe.
Thank you, Alan. I see that I was on mute.
Oh, yes,
Um, I will. I'm going to dive in on some of the technical parts. So Alan led with some of the considerations around this. I'm going to focus on specifically what we quantify and how we interpret what we quantify, really that last point. And then would love time for questions. So I'll share a few slides here. So for me, this got started just because someone asked me, how do we solve the explainability problem in machine learning? And the specific context for me is not generative AI, like so much of the rest of what we've discussed today, but when you go from regression models to machine learning models, a lot of things change, and I think in ways that are not fully comprehended or incorporated in the way we use machine learning models. Regression models have kind of smoothly growing uncertainty as you get towards the boundaries. Whereas a machine learning model in this high dimensional space, you can have pockets of predictability, pockets of uncertainty. And that's where we wind up with these discussions about explainability if you're on one of these boundaries between different outcomes and so forth. So to dive into that, I'll actually start with the answer. I won't make you wait through 6 or 8 slides to tell you what my conclusion is, but of course, explainability in machine learning models is a key concern. Local linear methods like Lime are criticized for being unstable near decision boundaries. And that's when people say, how do we solve the explainability problem? It's this boundary problem that keeps recurring. And so the question is, if the explanation is unstable, what do we do about it? I think if you reflect on this for a minute, think about these boundaries. What makes explanation at a boundary difficult? It's because you basically have a high curvature space inside your uh, large state space. There are areas of high curvature where it's difficult for a local linear approximation to explain what's happening. It's the curvature is the problem. But the curvature is also what causes areas of low predictability. So the way I have always thought of machine learning models is that they are great for finding pockets of predictability. But the corollary of that is you'll have zones of unpredictability. And and so these boundary regions, high curvature regions, can be these areas of unpredictability. And so if you compare these, where do I have explanatory instability? Where do I have forecast uncertainty? It turns out they're the same. And so the conclusion here is that we don't have an explainability problem. We have a forecast uncertainty problem. And the only problem there is not recognizing that we have it. So if you take a forecast from a machine learning model, then try to explain it and find your explanation is unstable, the explanation is not the problem. It's that you can't use that forecast. So let me try to motivate that a little bit. Um, Perhaps what I've just said is this view of instability at boundaries. And I should point out, piecewise linear models offer an explanation everywhere, but it's only actually true in the center of a region. If you have a piecewise linear model that looks like this, the region, the boundary region between those two has high uncertainty and forecast instability. I mean, explanatory instability. You can say what you think the explanation is because you have a linear model, but that does not mean it represents the true uh, state space, the true data. So claiming to have an explanation is not the same as having a reliable explanation. And it turns out that I'm not trying to knock piecewise linear models. I'm just saying that they're the same as all the rest. Piecewise linear models are not inherently explainable at the boundaries. If you optimize them well, the boundaries will coincide with these high curvature regions, which are exactly the reason that machine learning models in general become unexplainable at the same places. So the instability in explanation and the forecast inaccuracy for a piecewise linear model is the same as a machine learning model. Um, okay, so the real problem here is that the explainability problem in machine learning is actually a user problem, not a model problem. And what I mean by that is that we have, as an industry, been lazy because in the regression world, we largely ignore the uncertainty in the forecast. When scores are implemented, the only example I've seen of forecast uncertainty being incorporated is thin file versus thick file. You can get a bureau score and say, yes, but it's based on a small amount of data, thin file. Therefore, I will take hedged actions. I won't completely believe my forecast. It may say you're good, but I actually don't know much about you. I'll give you a starter product. If I have high certainty, thick file, then when I get that score, I'm fairly certain that you either do or don't deserve this product. And so I can commit to a, a larger loan, a more significant offering, or I can say more definitively, the answer is no. That is clearly one example. With machine learning models, you have that issue with every forecast because unless, I mean, if the forecast wasn't unstable across the state space, if it didn't have these pockets of high predictability and low predictability, then you ought to be using regression. You don't need machine learning models unless this is the very thing that's happening, that you have pockets of high predictability. So in that case, you need to know where are the pockets of high predictability, where are the regions of low predictability, and take actions accordingly. So the ML explainability problem is really an implementation problem that we need to go back to. I believe firmly any machine learning model that is implemented must provide both the forecast and the uncertainty, and decision making has to be on both. And if you don't do that, you're not using it right. I'm sorry, but that's the truth. So that is speaking to this kind of line-based framework. The punchline here is just that high root mean squared error is high uncertainty, which means it's an unreliable explanation and at the same time an unreliable forecast. Low root mean square error is low uncertainty, a trustworthy explanation. This is where you want to use your machine learning model. And I've just told you that you can't use your machine learning model everywhere, because if I measure the uncertainty and it says it's wide, then I really may not know what to do with it. You'll have to run tests. You'll have to see, can I get a usable forecast across the entire space of my model? There's a very good chance the answer is no, in which case you need a fallback. You may need your old logistic regression score as the fallback to take the place when the high dimensional machine learning model can't give you a reasonable forecast. Either that, or you have a fallback policy, equivalent to the thin file policy. If I have a forecast which has high uncertainty, I may have to offer a starter product. I may have to do something, but what I can't do is reject them using that high uncertainty forecast because I also have no explanation. If the confidence interval is wide, I don't have a good forecast, then I don't know why. So if you still want to rely on that model, you're going to have to be very careful about your decision-making process. Now, where you do have a usable forecast, you can measure explanatory instability. This isn't actually necessary, but it is a measure that will tell you how confident am I in my explanation. I say it's not necessary because if the confidence interval is small, then this will also be reliable. But the Hessian matrix is just the matrix of second derivatives. So what's the second derivative along each dimension of your state space? And the idea is that it's telling you the rate of change of the slope, so basically curvature. And where you get a high curvature, it means you'll have explanatory instability. Uh, and this has to be estimated, like anything else. So if you're estimating this from data, any of these things that have to be estimated, you can run out of data. So we don't want to pretend that there aren't computational challenges, but there are at least reliable methods for doing it. And through a part, I started with numerical simulations and said, well, let's compare the forecast instability you would get from a local linear model looking at the RMS error to um, the trace, the sum of the diagonal of a Hessian matrix. And that is the y-axis here. It's not a linear relationship because you've got um, that second derivative calculation and the square, the variability that's being computed, things like that. But it is a very reliable relationship. And I tested many different functions, and you're always in the 0.9 something percent range. And it turns out, I guess this is actually a table of some of those calculations. But the point is that, um, did I miss this? I guess I missed, in the paper that I have, you can actually prove mathematically that it's more than just a high correlation, that they're actually identical um, to within any kind of estimation error. The Hessian matrix is giving you an equivalent measure to the RMS error for a local linear model. So that's why you get these high R squared values. Um, I've already mentioned piecewise linear explainability is an illusion. It's only true in the center of a region. As soon as you get to the boundary, um, you have less certain in your forecast, as you are with any segment boundary. And of course, then you also have the transition possibly discontinuous between segments. So again, they're not inherently interpretable. That's mostly marketing. It's not the computational reality. And I think I've already mentioned the fallback plan. So I may stop here. I'll just read my conclusion that there's no explainability problem in machine learning. There's just a failure to measure and use the forecast uncertainty. And that's my key take home. Okay. I don't know if we have any questions, but Alan, if you have any questions, I can field those.
No, I mean, I like the way that you're tying up the the qualities of the model in many different aspects to uh, you know if a model is going to perform well, it's going to perform well in lots of different ways. If a model is not going to perform well, then it's going to fail on lots of ways together. So explainability feels independent from a lot of classical tests of stability and robustness, but actually uh, comes out to be part of the same mix. That seems to be a nice, powerful message that has generality at that sort of anecdotal level, but that there can be a mathematical background to that as well. Interests me greatly. In some sense, you're measuring, do you think there's a prospect for a common metric? I mean, there's always a danger in reducing any quality of a model to one dimension. Here we seem to be at least reducing the dimensions of model quality.
Well, I think we do have to make sure that for any model, we have a measure of confidence interval, which is kind of your one-dimensional metric. If we do that as the RMS error around a local linear model, the risk there is that I could, in theory, have a nonlinear model that was perfectly predictable, a perfect match to the data, and any local linear approximation doesn't do it justice, is unfairly discounting it because it's trying to be linear when in fact it's nonlinear. That's not usually the case. That's more rare. So I think the point is just we've seen people complaining about explainability because they jumped over the confidence interval question, the predictability. If you resolve the predictability question, then you'll find you don't have an explainability problem. Uh, you've already identified it via a forecast uncertainty problem. So we should probably leave it at that. I know people need to move to the next talk in the next minute, and I
No, thank
appreciate
you very
everyone's
much.
time.
Excellent. Thank you.